Hello there again, it's Matt. This week we are going to be talking about weight initialization. So in this case, like how to choose good initial weights for your neural networks. So this is a really important factor for successfully training your networks. If your weights aren't set right, then the backprop algorithm has a really hard time like getting to the minimum of the loss. So we're just going to go through this notebook, which we will provide for you on our public GitHub repo, so you can work through it too and see how all this works. Okay, so let's get started. So what we're doing here is just making a sort of really simple network for fitting to the MNIST data set. So MNIST data set, if you don't remember, is like a set of handwritten digits. And this is a really common data set used for like testing networks and testing performance because people know how it works. There's a lot of other networks that have been trained on this, and so you can kind of compare to those. And so this network is built in this helper script that is included with this notebook. So if you want to see how that was built, just look in the helper script and you can see how that was put together. But just like a really simple thing. And so this network is basically 3 layers. So you have your input and then 2 hidden layers and the output. And the output is just a softmax classifier. And then each of these hidden layers have ReLU activations, and then we're using an atom optimizer. So what I'm going to be showing you in this notebook and in these videos is that like how to set your weights appropriately. And this applies to other networks too, and not just the simple one on MNIST. Okay, so here is, just nice little diagram of the network we're using. So the first layer has 256 units. The second layer is 128. And since we're classifying digits, we have 10 output units. And we can see how we have defined our layers here. So again, we have the inputs. So this is the layer 1 weights. So from our input images to layer 1. So we have the shape of these images to 256, that's our units, 256 to 128, 256 to 128, and then 128 to the shape of our labels, which is 10. So it's the general layout of our network. So now we're going to discuss like how do you actually initialize these weights. So kind of the simplest idea for setting your weights is just set them all to 0 or all to 1. You would think that maybe this is the best solution, but it's actually kind of the worst solution. Sort of the problem is if every weight is the same, so say that they're all 0 or they're all 1, in that case, all of these units are going to be the same, right? Because like you're taking, your values from your input, you're multiplying everything by 0 and adding up. So all these are 0, and then all these are 0, and then all these are 0. And then you're comparing it. So again, like a softmax classifier using the cross entropy to get the cost, right? And then if you're doing backprop, all the gradients everywhere are pretty much the same because all of your activations are the same. And so then the network, like this backprop algorithm, has a really hard time trying to figure out how to set the weights or to update the weights and like calculate the gradients because everything, like all the activations are the same. So then all the gradients are the same, and then it just has a really hard time actually calculating the true gradient and getting down this loss function. And the same deal if the weights are all 1s, right? So if the weights all are 1s, then again, like you have your inputs all multiplied by 1 and added together, so all these units are again the same. So you have the same deal where all the units in this hidden layers are the same and like the output's the same. And again, like the backprop algorithm has a hard time actually trying to change the weights so that they fit the data. So what I've done here is I made 2 different, basically like 2 different networks. In one network, I've set all the weights to 0s. So TF variable, so these are all 0 weights. So these are weights. Variable, give them 0s. And then here I made another network that where all the weights are 1s. So all the weights are 1s. And then you can, using these weights of these different networks, you can like train on the MNIST data set and then look at the loss after some training, like look at the loss as it's trained. So this is basically a figure showing the loss, the network loss, over a number of batches that have been run through the network. So you can see like it starts out, so this is all ones, the blue is all ones and the red zeros. So you can see that it starts out high and the loss is like really large. Usually when you're running networks, you should have losses that are pretty small. Usually around like, I see them around like 1 or 2, right? Down here, we can actually see the validation accuracy. This is like 11% and this is about 10%, which means that our networks are basically doing guessing at chance, right? Because we have we are choosing 1 out of 10 classes. So if you're just guessing randomly, then you're going to get about a 10% accuracy. We can also see that the losses are really high, especially when everything's ones. So this is basically just performing really poorly. So again, because our weights are all the same, that means the activations of all of our units in the hidden layers are all the same. And then the backprop algorithm is just having a really hard time trying to like minimize the loss. So instead, what we can do is instead of setting everything all to zeros or all to ones, is that we want to have all of our weights with just unique numbers. And the best way to just grab a whole bunch of unique numbers is just to sample from some like probability distribution. And a good solution to do this is with a uniform distribution. Okay, so in the next video, I will show you how we can do this with a uniform distribution.